Okay, in a previous video we gave an example of a sequence of functions that converges uniformly, and now I want to give an example of a sequence of functions that does not converge uniformly. And we introduced a sequence of functions f sub n from the closed interval from 0, 1 to r, given by f sub n of x equals x to the n. And I claim that the sequence does not converge uniformly to f. And the issue has to do with what goes on for values of x that are close to 1, but not equal to 1. So let's think about what uniform convergence would mean. So uniform convergence in this case on 0, 1 means for all epsilon greater than 0, there exists some n such that for all little n and for all x in the interval from 0 to 1, the distance between f sub n of x, which is x to the n, and x, f of x would be less than epsilon. Right? That's the statement of uniform convergence of the sequence of functions. In particular, it would mean that for all epsilon, there would exist an n such that for all n and for all there exists some n such that for all little n greater than n, and for all x in the open interval from 0 to 1, the distance between x to the n and f of x, well, between 0 and 1, f of x is just 0, right? It's less than epsilon. So, i.e., and x to the n is always non-negative, so x to the n is less than epsilon. Well, is it true that for all epsilon, there is some integer n such that for all little n greater than n, x to the n is less than epsilon? Well, no, right? Because what happens is that x to the n goes to 1 as x goes to 1. So this is not true. So the proof that the sequence does not converge uniformly goes like this. So let epsilon be, say, 1/2. Okay? Then we know that for all integers n, there exists some x from 0 to 1 such that x to the n is greater than 1/2. Right? You just take x sufficiently close to 1 because, so the reason why this is true is because x to the n converges to 1 as x goes to 1. As x goes to 1. Right? And that's the proof. So the sequence does not converge uniformly on, actually we showed that it doesn't converge uniformly on the open intervals from 0 to 1. And so hence does not converge uniformly on the closed interval from 0 to 1. Right? I mean, if it converges uniformly on the closed interval, it'd have to converge uniformly on the open interval also, by definition of uniform convergence. And so that's the proof. And the idea can be illustrated by this picture, which is that what has to happen is that for every epsilon, okay, all the fn's eventually have to stay in this epsilon band, so to speak. This epsilon band. But we know that for all n, fn is going to look, it's going to start at 0, 0, and then eventually it's going to go outside because this thing has to approach 1. And so there's no n for which all the fn's eventually... Okay, how do I say this? There's no n such that fn values all stay in this epsilon band. Because eventually they have to leave the epsilon band to approach 1. To approach y equals 1. So that explains why this sequence of functions does not converge uniformly. Okay, I hope that clears up the distinction between pointwise convergence and uniform convergence. Uniform convergence is a much stronger condition, and it implies some nice theorems. It turns out that if you have a uniformly convergent sequence of functions, then the limit function has to be continuous. And as you can see, this sequence doesn't converge uniformly, and the limit function is in fact not continuous at 1. By the way, it would be a nice exercise to prove that this sequence of functions does converge if you restrict the domain to be, say, the closed interval from 0 to anything less than 1, so 0.9999, right? So a good exercise would be to show that the sequence given above does converge uniformly on the closed interval from 0 to a if a is less than 1, strictly less than 1. Okay, thanks for watching.